Hello, welcome back. So last time we talked about, again, the idea is how to use the Fourier transform practically on a digital computer or digital signal processor. So last time we talked about basically this idea of simply using finite sums. So you have a summation with n samples or n points, which makes sense practically because by the end of the day you will not wait for eternity to basically to collect all your samples. But of course there is a price to be paid, and the price to be paid is that if you truncate your summation, it's as if you multiply your signal in the time domain by a window which is like a signal with a finite support from small n equals 0 to small n equals big N minus 1. And when you do so, the spectrum is convolved with the spectrum of the window. So if the original spectrum should be a Dirac delta, you don't get a Dirac delta anymore. You get basically this aliased sink in the frequency domain, which is not a Dirac delta. It's a thing with the main lobe and then side lobes. And so we talk about how to deal with the issue of side lobe suppression via the Slepian window. Now, another thing is the frequency variable in the DTFT. So even if you truncate the summation, okay, so what is the DTFT of x of n? Well, that is equal to summation. So suppose that you truncate, okay, so let's say that you will actually multiply by a window, okay, and so this will be, the window is non-zero only from 0 to n minus 1, but then you have this here, and so you have, this is a continuous vector, okay, so it means that, how can you deal with something like this? There is like an uncountably infinite number of points in each interval. And so, like discretization in time, we will now try to say, well, we will have to compute or care about the spectrum at specific frequencies. Okay, and so that's it. We need to sample the spectrum. Okay, and by doing this, we will have a finite, as we will see, we will have a finite number of samples in the time domain and a finite number of samples in the frequency domain, and those are manageable. You can basically play with them, do processing, transmit them, store them, and so on. Okay, so the idea now is how to sample in the frequency domain. So we want a signal x tilde of n, which comes from x of n by sampling its DTFT. And we will sample, again here in this course, we mainly focus, at least in the lectures, on uniform sampling. So we will take a sample from the DTFT every f0 hertz. Okay, so I will take a sample at f equals 0, at f equals f0, at f equals 2f0, at f equals 3f0, and so on. So we will do uniform sampling, take the value of the DTFT on a particular grid with a spacing equal to f0. And mathematically, this means that we will model, we will take the original DTFT, and it's as if we multiplied by a train of Dirac deltas, and those Dirac deltas are spaced by f0. Okay, again, which is the mathematical way of basically modeling the sampling process. But there is one technicality here that we need to think about before we move, which is, now you are sampling the DTFT of a signal that in time is already a discrete signal, and it is defined on a grid with interval Ts. And from the definition of the DTFT, if you look at this factor here, you will find that the DTFT is always periodic, and its period is Fs, which is 1 over Ts. And so when we sample the DTFT, we want to do so such that we get a sequence, and this sequence is periodic. So we want the spectrum also to repeat every Fs. Because if we do not do so, then then our signal in the time domain becomes something, other than the signals that are sampled every TS. Again, every signal that is sampled every TS, its discrete time Fourier transform by definition from the formula for the DTFT. It has a DTFT that repeats every Fs. So we want to sample the spectrum and preserve this periodicity. We want also the resulting sampled spectrum to repeat every Fs, so we do not want to play with the signal in the time domain by making, by changing its nature. We still want x tilde of n to be a signal that is sampled every Ts. And so to sustain the periodicity in the frequency domain, it must be the case that the interval of sampling, f0, must satisfy that fs over f0 is equal to an integer, right? So here's the frequency axis. You take a sample at 0, you take a sample at f0, you take a sample at 2f0, and so on. And then there is here the value fs. Now what you want to do is that you want to take a sample at Fs also, so that your spectrum is repeated. So you get a periodic sequence that repeats every Fs. So to do so, we need Fs needs to be V, where V is an integer, F0. If you don't do so, you get a spectrum that is not periodic with a period Fs, which means that the time domain signal is anything but not a signal that is sampled over Ts, that is sampled every Ts seconds. Okay, so again, the idea, when you started sampling in the time domain, we do not care about this because, like, your starting point is a continuous time signal that you sample. But now we have a discrete time in the time domain, and we are sampling its DTFT. And its DTFT is periodic, and we want to sample such that the periodicity is preserved. And so we need to have Fs equal to an integer multiple of F0. So Fs over F0 is equal to V, can be 1, 2, 3, and so on. And, we will follow the convention because this V will be fixed later. But generally speaking, you can choose any V of your choice. You can do something as silly as taking a sample at 0, at Fs, at 2Fs, and so on. Okay, but it's not a good idea. And again, we will settle regarding a specific value of V that is used in applications and in the definition of the DFT. Okay, before moving, we will need the DTFT of the shifted Dirac delta by Kf0. Okay, so what if you have a Dirac delta at Kf0? Again, you can just apply the formula for the inverse DTFT, and the result that you will get will be 1 over Fs e to the I 2 pi Kf0. Okay, so that's the location of the Dirac delta, NTS, and then from here we know that, so you get F0 TS. And what is F0? F0 is equal to Fs over V, TS, and TS and Fs are the reciprocals of one another, and so this is 1 over V. And so you get, basically in simplified form, you get this factor 1 over Fs e to the I 2 pi Kn over V for K from 0 to V minus 1 again. Those are, so here we take samples, we will place Dirac deltas at 0, at F0, at 2F0, all the way to V minus 1 Fs. And we will need to take the inverse discrete time Fourier transform. Just from the definition, basically this is the inverse, and the exponential now is written in terms of V, again using basically this result, that F0 is Fs over V, and the other result that Fs by definition is 1 over Ts, and so their product is unity. Okay, so here is how we do the investigation. Same story like sampling in the time domain. So it's basically the same idea, which is you construct a sampled DTFT. How do you do that? You take a DTFT, which is a function of the continuous variable f. You multiply it by a train of Dirac deltas. Now those are Dirac deltas in the frequency domain. We are doing sampling in the frequency domain, and they are spaced every f0 hertz. And f0 is not arbitrary. Fs over f0 must be an integer. And here we are using this scaling factor to basically to follow the convention. You may have it or not, this f0 outside, you may eliminate it and your math will be correct, but basically things here are written so that we get finally at how the discrete Fourier transform is defined in signal processing. Okay, and when you multiply a function by a train of Dirac deltas, well, you have two options. One option is to leave the product as this, and the other option is to use the property of the Dirac delta, which is that if you have a Dirac delta, if you have a Dirac delta at Dirac of alpha minus alpha 0 and you multiply by G alpha, this actually evaluates the function at alpha 0. Okay, so the second option is to take this function of frequency and insert it inside the summation and evaluate it at kf0. Then you do what? Then you do the inverse discrete time Fourier transform. You do it for this and you do it for that. Okay, so again, this is like sort of the way of sampling any any variable. You have a function of a certain variable, let's say an abstract variable alpha. Okay, and so what you do is that you multiply by a train of Dirac deltas, and here I'm talking about uniform sampling every delta, and then you equate this thing to basically G of n delta, big delta alpha minus n delta. Okay, and then you do the Fourier or inverse Fourier transform. You use the continuous or the discrete based on what signals you are talking about. So this is a very general idea, and then you do the Fourier transform in two ways, and you equate them, and you get basically some understanding of what sampling is doing. The only thing here, is that the separation in frequency by f0 to produce a signal that is also periodic with the period fs over f0 must be an integer. Okay, so that's the only constraint. But this is a general framework for converting a G of alpha, where alpha is a real parameter, to G of n, G of n delta. Okay, so what we will do here is that we will take the inverse discrete time Fourier transform, our new signal. So x tilde is the signal whose spectrum is the spectrum of x of n, but now it is multiplied by this train of Dirac deltas. So x tilde of n. What is the inverse Fourier transform of this product? So we have the convolution theorem. So the convolution theorem tells you, well, the inverse DTFT, it is the DTFT of, it's the inverse DTFT of the DTFT of x of n. So that's x of n. Product becomes a convolution. And you do basically the inverse DTFT of those Dirac deltas, and it will give you those exponentials as explained here. And of course, there is an assumption, so basically this is an infinite sum. So you are basically doing the inverse DTFT term by term. Yes, I am doing so, assuming that what I am doing is valid. So we can interchange the order of inverse DTFT and infinite sum. But you can also do the inverse DTFT to the other form. In the other form, we have, this is a constant, because once you multiply by the Dirac delta, you get this function evaluated at kf0. And then when you do the inverse DTFT, you do the inverse DTFT of the shifted Dirac delta, which gives you again this guy here. And then you say that mathematically speaking, you should have equality, and so this is equal to that. Now, let's manipulate this thing. So let's talk a bit, because this function is very important in DSP, digital signal processing, and DFT, and so on. So what is this thing? You know, let's spend a couple of minutes talking about it. Again, it's so famous, it appears a lot. This is a summation with an index k going from 0 to v minus 1. So we have v terms in the summation. We divide by v, and then what we are summing is e to the I 2 pi k. K is the index of summation. N, so your result will depend on n, which is another integer, over v. V is the number of terms in the summation. Okay, so a very famous sum, very useful. Now, what is, so again, you end up with a function of n, right? Because you sum over k, so k will disappear once you do the summation, and you end up with a function that depends on the integer n. So there are two possibilities. One possibility is that n is an integer multiple of v. So again, there is a fixed v, and it basically represents the number of terms in this summation, and it's also here. Now suppose that n is an integer multiple of v. So it is equal to 0, or v, or minus v, or 7v, or minus 13v, or something like this. Now, if n is a multiple of v, then replace n by lv, where l is an integer, v goes with v, and you have e to the I 2 pi multiplied by an integer, and this is always equal to 1. And so your summand becomes 1. You sum 1 v from k equals 0 to v minus 1. So you are summing 1 v times, you get v. You divide by v, and so you get a 1. So now this summation here, if n, it's the free parameter, so basically your output is a function of n. If n is an integer multiple of v, if n is divisible by v, then this summation here, together with the scaled factor, it gives you exactly 1. So it's 1 if v divides n. Now what if n is not a multiple of v? In that case, you can rewrite things as if you have a geometric series, right? So you can take this guy here and write it as e to the I 2 pi n over v raised to the power k. And then you have a finite geometric series, you apply the formula, and then you get this result. Now look at this result. In the numerator, you will have the ratio of the geometric series raised to the power of the number of terms, which is v. So this will lead to e to the I 2 pi n, which is 1, and we have 1 minus 1 in the numerator. In the denominator, we have e to the I 2 pi n over v. Remember that n is not a multiple of v. So this exponential here is not equal to 1, and in the denominator we don't have 0. So we have 0 over a non-zero quantity, which is exactly equal to 0. So this summation here, again, extremely important and very useful in DTFT, in DFT, and in digital signal processing in general. This summation is basically a periodic sequence, a periodic discrete time function that is equal to 1 at the integer multiples of v, and that is equal to 0 otherwise. Okay, so we can write actually this summation here in terms of the shifted discrete time deltas. Okay, so by writing things in this summation, we are basically saying that we have a 1 if n is LV, and we have a 0 otherwise. Okay, so keep this in mind. And now when we do the convolution with the discrete time delta, we just get the shifted versions of the function x of n. Okay, so again, you know from basic signals and systems that, you know, if you convolve x of n with the discrete time delta n minus n0, you get x of n minus n0. Okay, and so this is the result that we get. So the result that we get is x tilde of n. What is this guy? This guy, you start with an x of n. X tilde of n is the signal in time whose discrete time Fourier transform is the discrete time Fourier transform of x of n, but multiplied by a train of Dirac deltas spaced every f0. In other words, x tilde of n has a DTFT that is a sampled version of the DTFT of x of n. So in the time domain, how is x tilde of n and x of n related? X tilde of n is a periodization of x of n, right? So this is what we learn. So x tilde of n is equal to, if n is 0, it is equal to x of n plus x of n minus v plus x of n minus 2v, and so on. It's also plus x of n plus v, and so on. Basically, when you sample the spectrum, you get a new signal in the time domain, which is basically the original x of n, but actually it is shifted at all integer multiples of v and added. So basically, x tilde of n will give you this periodization of x of n. X of n is replicated at all integer multiples of v, and then you have a sum of all those replicas. So this is what happens in the time domain if in the frequency domain you multiply by the train of Dirac deltas. And what is the other side? So the other side is basically the DTFT of x of n evaluated at kf0, which here I will denote by big X of k. And again, this is just the Dirac delta, and it is evaluated. It is the DTFT of x of n evaluated at integer multiples of f0. And don't forget that f0 is the sampling interval in the frequency domain, and it is not arbitrary. Fs over f0 is equal to v. Okay, so what? I mean, so what is really the relationship between x tilde of n and x? I mean, you see that for many signals x, if you play this game, this summation will explode. So suppose that x of n is equal to 1 everywhere. Then basically you take this one everywhere and shift it at all integer multiples of v, and sum, you will get infinities. Okay? So, you know, for many x of n's, basically this periodization will make no sense. But not for, you know, for example, if x of n is just a time-limited signal, if it has a compact or a finite support, then this periodization actually may not be bad at all. So let's see what I'm talking about here. Suppose that this is your x of n. So it is, so basically, what is this x of n? It's time limited. It's non-zero over a finite support. Here basically n in 0, 1 to n minus 1. And in this example, I am taking big N to be equal to 4, which means that x of n is just those 4 samples, otherwise it is equal to 0. So these 4 samples, again, you can go and compute their DTFT, just using the definition of the DTFT. So now what will happen if the DTFT of this signal is multiplied by train of Dirac deltas that are basically, separated by f0 now, and let's choose basically f0 to be fs over 4. Okay, so here f0 is equal to fs over 4, so v is equal to 4. So basically the sampled signal, okay, which, above I'm denoting it by x tilde of n, so it is a summation of this thing here, okay, L is an integer, every v, and v is 4. So basically what you get will be that those 4 samples will be shifted to the left by 4 samples, to the right by 4 samples, to the left by 8 samples, to the right by 8 samples, and so on, and then you sum them together, and what you get is exactly this. See, when you make v equals n, so if your signal is time limited, it is non-zero only from 0 to big N minus 1. If you choose v to be equal to n, what is the impact of sampling the DTFT? Well, the impact is sort of minor. What you get a new time domain signal, but this time domain signal is periodic, and it is specifically the periodization of the original signal every big N when we choose v equal to big N. The formula is that you periodize every v, and this is a special case when I choose v to be equal to big N. Note that in this case, okay, there is no aliasing. So when you shift the x and add, there will be, the replicas will not interfere with one another. You do not need v to be equal to n for this to happen. You need v to be greater than or equal to n. However, as a matter of convention, and this is how the DFT is defined, we will choose v to be equal to n. We will fix it. Okay, so again, just to make sure that we understand what we are doing. Suppose that you take this example and you choose v to be equal to 5 rather than 4. What will happen? What is x tilde of n? So it will be x of n, but then 0, and then it will be x of n again, and then 0. Okay, so let's, and then 0, and so on. So basically the replicas will not interfere, and you will get those zeros here. Okay, what if v is equal to 6? No problem. Those replicas will get far and far apart from one another, but they never, basically they never interfere with one another. Okay, again, because the signal has a finite support, and the shift has basically a value that is greater than or equal to n. But again, the convention is that we will use v equals to n, which means that the sampling interval in the frequency domain is fs over n. So this will be a choice, is fs over n. So because again sampling the spectrum means that your signal in the time domain will be periodized, we will assume that the signals of interest to us are time-limited signals. Signals, discrete time signals, with a support, and we will take it again by convention to be they are not potentially non-zero from small n equals 0 to small n equals big N minus 1. The effect of sampling the spectrum is to periodize, and there is no harm if v is greater than or equal to big N, but we will just fix v at big N, and hence our DTFTs will be sampled every fs over big N. Okay, so this is basically a choice that we will fix. Like to have a better feeling of, so what if you choose v less than n? In that case, there will be aliasing. Let's see. So suppose that v is equal to 3, and in our case here, n is equal to 4. So this is our example signal. Now, according to this is x tilde of n, and what is x tilde of n? It's the summation of x of n L v, which now will be 3, and L is an integer. So we shift to the left and to the right by all integer multiples of 3. Now, when you do these shifts and add, you know, the replicas overlap. See, this part here, there is a sample here. When you shift this signal by 3 samples to the right, you know, you have this sample interfering with this sample at 3. And so when you add, because x tilde is the addition of those replicas, you get something that looks like this. 5, 2, 3, 5. Now, as you can see, the original signal on n 0, 1, 2, 3, it was equal to 1, x of n was 1, 2, 3, 4. Now, at 0, x tilde of n is 5. At 1, it's 2. At 2, it's 3. Okay, so those are not basically changed. But then at 3, it is equal to 5 again, and so on and so forth. But the idea is that you have aliasing. So this, you know, this overlap between the replicas is aliasing. But again, it's like what you studied in the, you know, when you studied sampling theorem in a previous course, it was a signal in the time domain, and when it was sampled in the time domain, its DTFT was periodized. And we tried to find a condition such that the replicas, the aliases, do not overlap. And this gave basically, this yielded the result that, you know, Fs is greater than 2W, this sampling basically result. Now we are basically sampling in the frequency domain, okay, and things become periodized in the time domain. And we discovered that basically to avoid aliasing, to avoid basically that the sum, this sum will have basically components that interfere, we need v to be greater than or equal to n. Now we will just do something. We will fix v to be equal to n. Now, this is very nice in the sense that now, so now this is the frequency axis. So you take a sample at 0, you take a sample at f0 now is equal to fs over n. This is f0. And then at 2 fs over n. And then you go all the way to n minus 1 fs over n. And then this is at fs. But we know that the DTFT repeats every fs, which means that the DTFT here is the same as the DTFT at 0, at f equals 0. So effectively, when you sample the DTFT and you basically use fs over n, how many samples do you really need to compute and store and transmit and so on, if needed? Just those guys, exactly. And this is the magical number, n. So basically, those n samples are repeated. Okay, so you just need to care about n samples. So now, by fixing v equals n, we have to care about n samples in the time domain. Okay, because again, we will basically assume that we have time-limited samples, signals, and even if our signals are not time-limited, we will basically pretend that they are time-limited. Okay, we will just take n samples and do processing with them. Okay, so n samples in the time domain and n samples in the frequency domain, and this is sort of cool because, like, now there is sort of a symmetry. When you choose v equals n, it's like now you have to deal with, there are like n numbers, n generally speaking complex numbers in the time domain, and n complex numbers in the frequency domain, and you can go back and forth between them. Okay, so basically this sort of symmetry, n numbers on one domain and n numbers on the other domain, is again, it's an appealing thing. So that's, you know, one also motivation that you fix v equals n. If you fix v equals n, now when you sample the DTFT, and given that the DTFT repeats every fs, basically the number of values you need to compute are just n of them. Give me the value at 0, fs over n, 2 fs over n up to n minus 1 fs over n, and you know, basically those values will keep repeating again and again and again, because we are sampling a spectrum that is already periodic and repeats every fs. Okay. So from a practical point of view, now the good news is this. Now, like you do processing, you have to deal with n samples in the time domain, n samples in the frequency domain. A finite number of samples in both domains seems appealing, but we need to understand exactly what we are doing. Okay, so again, it's like there is always a price. So for example, like to take your signal and to pretend that it is a time limited signal just defined from n equals 0 to n equals big N minus 1. So we talked about this in the previous lecture. It's like, you know, again, if your signal is a complex sinusoid, now forget about getting a sharp spectrum at its frequency. You will get this main lobe and side lobes and so on and so forth. Now, if you want to just deal with n numbers in the frequency domain, again, computationally, this looks very appealing. You don't need, like, you have to deal with just n numbers. But what is the impact of this? So we will start being exposed to the consequences of what we are doing, because this may need, like, we need like to tweak our algorithms to basically reflect, you know, basically our assumptions. You know, that what we are doing, we are changing things, and we need to basically keep track of those changes, as we will see. Okay, so that's basically the story of the previous slide. We take a sample every fs over n. We can take a sample every fs over v with v greater than or equal to n, but we will fix v equal n. Now, your discrete time signal, you know, we will assume that it is basically something that is potentially non-zero from 0 to big N minus 1. Now, when you discretize the spectrum, this signal will be periodized in the time domain. You will get an n periodic signal, and we got basically this relationship here. And this relationship here, sometimes it's called the discrete Poisson summation formula, and it is very useful, and you can make use of it, as you will see in the problem set. And this x of k is the original DTFT evaluated at kfs over n. So now we will no longer deal with a continuous frequency variable. We will compute the spectrum every you know, integer multiple of fs over n, and we need to just to compute n numbers, because the numbers will keep repeating. Okay, so here is basically what we have till now. Okay, so so this is you know, so this is x tilde of n. It is given by this summation here. And what is x of k? Again, x of k is DTFT of x of n evaluated at kfs over n, and k equals 0, 1, 2, n minus 1. And so that's the definition of the DTFT, right? And you do basically this, you put f equals this quantity, and you get this. Okay, so we have like x of k related to x of n, x tilde of n related to x of k, and we have like here a plus sign and here a minus sign. We have things like they are candidates of being a Fourier transform pair, perhaps a new type of Fourier transform. Okay, because now like every our signal is discrete in time and is discrete in frequency. So if you choose v, so if your signal is really time limited and you choose v equals n, then x tilde of n is equal to x of n over this range, right? So remember, x tilde of n, it's written here, x tilde of n is equal to this summation here. Okay, it's the periodization, and x tilde of n is equal to x of n for n in 0, 1, 2 to n minus 1, assuming that 0, 1 to n minus 1 is the support of x of n. So it is potentially non-zero just for those values. Okay, so you can basically rewrite this thing with x tilde of n, and so now you have what looks like very much like so x tilde, and big X. Okay, we have a transform pair. So that's the discrete Fourier transform. The discrete Fourier transform is basically a Fourier transform that operates on n points or samples in the time domain, n points or samples in the frequency domain. It is not something that is, you can explain it, you can just write down those sums and, try to pretend that they come out of thin air, but they are related to the DTFT. And, this is the story behind them. It's basically a sampling process in the frequency domain. But here is one annoying thing, okay, but again, we need to follow convention. I will rewrite the DFT using x of n. I will just use the symbol x of n with the understanding that we actually mean x tilde of n. Annoying, but that's the DFT. Okay, so this is how it's formally defined. So what I did is that I took our previous results, which are sort of, again, multiply by Dirac deltas, do the inverse DTFT, now set parameter v equals to n. So we did these things, we did basically these steps, and the relationship should be between like sort of big X of k, which is the DTFT of x of n evaluated at kfs over n, and the periodic signal x tilde of n, which is a periodization of x of n, but we will write down this. So this is the discrete Fourier transform pair. This is the discrete Fourier transform. X of k is equal to summation n from 0 to n minus 1 x of n e to the I 2 pi k n over big N. And the inverse will be x of n is 1 over n summation k from 0 to big N minus 1 x of k e to the I 2 pi k n. And this is called the n point d. The word point here is just to mean n samples, n numbers, n generally speaking complex numbers. You have n complex numbers in the time domain, n complex numbers in the frequency domain. So we will write down things like this, but we know actually that what we mean is x tilde, the periodic signal, not the time limited signal. But we will write it like this again because this is the convention. Okay. Note the following, that if you write down something like this, both x of n and big X of k, both of them are mathematically periodic, no matter what you do. So that's the reason, like, suppose that I just write down for you these two expressions, and I tell you examine the periodicity of small x and big X. So they are sequences, they are discrete sequences. One of them depends on n and the other depends on k. Examine their periodicity. Let's see. So you can examine x of n plus big N. So you replace this small n by small n plus big N over big N. This exponential is this one, and what is this one? 1, right? So from these formulas, there is no way, and you can do the same for x of k. Both sequences are periodic. In other words, if you try to compute small x of n and big X of k at values other than or outside the range from 0 to big N minus 1, you will basically get a periodic signal. So what is small x of big N? It is a small x of 0. Okay, so if you have two signals that obey these two sums, they must be periodic. There is no escape. I mean, it's inherent in having those exponentials here and there. So this is small x that you put here is periodic. So what is the meaning? What is the meaning? Because okay, so when you do processing, suppose that you actually have a signal that is time limited, and it is defined just from 0 to big N minus 1. Once you take this signal and you take its DFT, it's as if you are periodizing the signal. So the mathematical machinery of DFT and IDFT, again, so even if your signal, and actually this is the thing, I mean, you take n samples and you insert them there. Okay, so you insert them here. Those are the n samples, and your summation is just n terms. Guess what? If you have these small x of n and big X of k related using these two sums, both small x and big X are periodic with a period n. So in reality, it's as if you have a time-limited signal, but once you play with it using the discrete Fourier transform, it becomes periodized. So that's the reason, if you want to be very accurate, the x that should appear here is x tilde, which is the periodization of x of n. But I will write it like this because this is what you'll find in the references. Okay, so again, writing it with x tilde has the advantage of telling you that you start with a time-limited signal, but then what you have here is a periodized version. Okay, and it's very clear because you use x and x tilde, a different symbol. But the practice is, in the literature, is that we'll just use x. So you take n samples and you put them in the DFT machinery. Those sums, you play with them. As we will see, we will use the DFT to compute convolutions and stuff like this. You get up periodicity. You are forced to basically to periodize because of, how can you write down an expression like this and claim that x of n is 0 outside the range from 0 to big N minus 1? Does not make any mathematical sense, because if you write down an xn that looks like this, x of small n plus big N is equal to x of n for every integer n, period. There is no way out. Okay, so this is very important. Okay, this is very important, and it actually has, consequences for the practical uses of the discrete Fourier transform, and we will talk about some of them. Our signals in time, of course, the sampling interval is Ts, and now the sampling interval in the frequency. So if you are talking about absolute time or absolute frequency, Now our signal is discrete in time. There is a sample every ts seconds, and our signal is discrete in frequency, and we take a sample every fs over big N hertz. What are some of the properties of the discrete Fourier transform? So x of n, small x of n and big X of k that are related by this two sums. Well, I mean, you can basically apply the definitions. If your x of n is just delta of n, if your x of n is just delta of n, okay, so here I am defining, so delta of n, n from 0 to big N minus 1, then x of k will be equal to 1, right? And because this is the discrete time Dirac, and the discrete time basically the discrete time delta, it is 0, so it is 1 if n is equal to 0, 0 otherwise. So it will give you 1. It will give you 1. Note that if you take the inverse, take the IDFT of 1. So what will happen if you take the IDFT of 1? Let's do it. By definition, it is 1 over n summation k from 0 to big N minus 1 of 1 e to the I 2 pi kn over big N. What is this? This is the summation we talked about at the first part of the lecture. It's very famous. So you sum over k, you get something that depends on n. This is 1 if n is equal to 0, plus or minus big N, plus or minus 2 big N, and so on, 0 otherwise. 0 otherwise. It must be periodic, right? So if you try to play this game in which you say, okay, I will take a signal x of n that is just equal to 1 at n equals 0, if you do the DFT, which is this summation, you will get all ones. Now, if you do the inverse DFT, you will get a 1 that is repeated every integer multiple of big N. Is this a contradiction? No, it's not a contradiction. It's basically it's this annoying matter, which is that basically the DFT should be something like this, related to the periodization of x of n. But we will write it as in terms of x of n. Okay. But I mean, I hope this example. I mean, again, start with a signal that is just 1, and try to pretend that it is just 1 at n equals 0, and it's 0 everywhere. Take its DFT as defined. Don't even ask why this summation, how it was basically derived or anything. Just take it for granted that someone invented this thing called the DFT sum. Take the DFT of this delta of n. You get a 1. You say, okay, fine. Now employ the inverse DFT. Will you get a 1 just at n equals 0? Impossible. Impossible. Because of this, impossible. You will just get this one periodized. Okay, so basically what you get is x tilde of n, But forget about this, because again, like once you go and use the DFT, you understand this issue. But I mean, you don't deal with an x and x tilde. Okay, you just deal with an x, and you understand what is going. If you take a function that is from 0 to n minus 1, it is forced to be periodized, which has practical consequences, because like you take a function and it's living just somewhere on the n-axis, but then it becomes as if it's repeated everywhere on the axis. This will have consequences. They are coming. What if x of n is equal to a constant 1? Again, you apply this is summation k. This is x of n. So you do the DFT, and if your signal is 1, if all the n samples are equal to 1, then the DFT will be n if k is equal to 0 or an integer multiple of n, and 0 otherwise. Rules. The rules are very similar to what you have for other types of Fourier transform. So time shifts, for example, become multiplication by exponentials. So let's do this one. What is the DFT of x of n minus n0? Well, take x of n minus n0, insert it here. Okay, insert it. Now, you want to write down this summation in terms of the DFT of x of n without a shift, with n0 equals 0. So what's the way to go? As typical in Fourier analysis, you will do a change of variables and say, well, I will define small m equals n minus n0. And basically you change every small n to small m plus n0, and you also need to change the upper and lower limits of summation. You will get something that does not depend on the summation index m. You can bring it outside, and this is the famous exponential that appears whenever, like, you have shift in one domain, you get exponential in the other domain, but then you get this summation here. Okay, so let's look at this summation. M e to the minus I 2 pi km. What is this summation? What is this summation? Okay, so it looks like it's not the DFT, but it is the DFT, right? So this summation, it goes from minus n0 to n minus 1 minus n0. So basically, you have n terms in this summation. It's not from 0 to big N minus 1, but who cares? What you are summing is periodic. So this is an idea to keep in mind when you do manipulations with the discrete Fourier transform. Now, this guy, you can check that it is n periodic. And this, the function that we involve in the DFT, it is n periodic. It should be x tilde. We will write it as x. It is n periodic. And if you multiply two sequences that repeat every big N, you get a sequence that repeats every big N. So now, suppose that you have something that repeats every big N, and you sum big N terms. It won't matter from what index you start your summation and at what, so long as you take in some N samples, right? So because of this, this is exactly equal to the sum from 0 to big N minus 1. So this is something that to keep in mind, because like when you do proofs for the DFT, you typically do change of summation index, and you will find that your summation is no longer from 0 to big N minus 1, not a biggie. Okay, if what you are summing is a sequence that repeats every big N, then you can do the sum any way that you wish. You just need to go from, let's say, 0 to big N minus 1, or based on whatever is convenient in your derivation. Any question? Other properties. Time reversal. So what is the DTFT of x of minus n? Same story. Write down the definition of the DFT. Use the index small m equals minus n. It will change the limits of summation, but then you are summing something that repeats every big N, so no problem. I mean, you can shift the indices by making them from 0 to big N minus 1, and you get this summation. So what is this summation? It looks exactly like the DFT, but with a plus sign here rather than a minus sign. So this is x of minus k, which means that the DFT of a time reversed signal is like the DFT of a frequency, is the reversal of the original DFT. DFT of x of minus n is x of minus k. Okay, so this again, you find this in the CTFT, DTFT, it's also in the DFT. Now, this is important, like when you, if you use the DFT a lot in your work, is like, so typically on a computer you will have your n samples like in a row vector, in a column vector. What is x of minus n? What is this basically time reversed signal? So what is x of minus 0? It is x of 0. What is x of minus 1? What is x of minus 1? Again, don't say my signal x, it's from 0 to n minus 1. No. Once you start using the DFT, you are dealing actually with x tilde. And so this is x of n minus 1. What is x of minus 2? This is x of big N minus 2. You periodize. Now your signal appears that it repeats itself every n samples. Okay? So what if you have a vector like this and your signal, again, because like in applications, you typically think of x as if it's a column vector with n samples. So what is the vector corresponding to x of minus n? So x of 0 is x of 0, because x of minus 0, x of minus 0 is x of 0. And what is x of, x of minus 1 is, so if you put n equals 1, it is x of big N minus 1, x of big N minus 2. And so if you compare these two vectors, time reversal is like this. So you have, this is your original vector. Time reversal, it's as if fix the first guy, take the other n minus 1 samples, and flip them upside down. Sometimes this is like nice to understand what you are doing if, again, you use the DFT in signal processing. Now, if you basically represent your n samples using a row vector, then x of minus n is like you keep x of 0 in its place, and then you flip the remaining n minus 1 samples left, right. Okay, so so those are like the flip up, down, and flip left, right instructions in MATLAB. Okay, so again, it's sometimes useful to think of time reversal like this, because like when you have like signals, you are dealing with them in using DFT. It's like you typically want to describe things using the indices from 0 to big N minus 1. So basically x of minus 1, it's annoying to think of it as x of minus 1. It is x of big N minus 1. Okay, so basically you shift things so that you always talk about the indices taking values from 0 to N minus 1. Okay. What if you take the DFT of the DFT? Well, if you take the DFT of the DFT, again, questions as such are to be answered by using the definition. Okay, so what is the DFT? So the DFT, I take a signal. I take basically a signal, okay, and now this signal will be so this is the DFT of x of n. I am writing it like this: summation m from 0 to big N minus 1 x of m e to the minus I 2 pi k m over big N. I just use the index m, which is, you can use whatever index of your choice. The only choice that is prohibited is that you do not use k, because k is already used, and the output of your DFT is a function of k. So I used m. So what is this? What is this thing? This is the DFT of x of n. Now I will take its DFT. I will take its DFT. What do I mean by this? So if you have a signal psi that depends on index in index v, what does it mean that I take the DFT of the sequence? Okay, so sometimes you need to think in abstract ways. We typically use n for time domain, k for frequency domain, and so on, but don't be like stuck with these. Again, because this may confuse you when you are trying to answer questions like this. If you have a sequence like this, what is its DFT? It means you have a summation. You sum those samples. After multiplying them by what? E. You are doing DFT minus, this is what we will use here, and it's the definition of DFT in signal processing. I, 2 pi, the same index, V, over the number of terms in the sum, big N. Then you need to choose an index to describe your output. I can call it S. So that's the DFT. And this will be computed for S0, 1, 2, up to big N minus 1. Okay? So when I ask myself, what is the DFT of the DFT? It's a mathematical question that makes perfect sense. That makes perfect sense. Okay? So if this is confusing you, then you need actually to do some self-reflection. Okay, it means that you are still attached to things like time domain and frequency domain. And you know, what does it mean that I go from time to frequency, and then in the frequency domain I do the Fourier transform again? You know, those are just mathematical operations. And sometimes, you know, it is really important that you think of them as just the black boxes. In the case of the DFT, it's like you give the black box n complex numbers, you get output n complex numbers. The meaning of those n complex numbers, whether they are time domain or frequency domain or whatever domain, it's up to you. But from the point of view of the black box, from the point of view of the digital signal processor doing the computations for you, those are just n numbers, not attached to any like physical coordinate. Okay, very important to basically have this understanding. So I want to take the DFT of x of n. You know, well, I mean, I take the samples x of, I call this index m. I can do so. Why not? I then move this index from 0 to big N minus 1. I am doing DFT. Cool. I will multiply by e to the minus I 2 pi, and then I need to have this index. I need it to be up there, divided by big N, which is the number of samples or the number of terms in the summation. And then I need an index that is different from M to specify my output. So now I have something that depends on K. I want to take its DFT again. Not a problem. Summation. K from 0 to big N minus 1 of this thing that depends on K. You want the DFT? Okay. E to the minus. Why minus? Because I'm doing DFT, not an inverse DFT. I am doing DFT, so minus I 2 pi, and then this K appears here again, and then you choose a name for your output. It can be N, as I am doing here. It can be anything that makes sense. You cannot use K, you cannot use a small m because it's already used. If you want to call this a small n R, you are fine. Okay, so again, make sure that if I tell you DFT of x of n, you can comfortably write down this double sum and it makes sense to you. Let it take whatever it takes. Okay, so you can write down things like this comfortably without like not being annoyed by anything. Now, how do we do this double sum? Well, I can basically collect the terms with a K, and guess who we have here? It's our famous summation now. We did on the first page. Summation, index, 0, n minus 1, a big N here, the summation index there, and then some other integer. This summation is equal to the number of terms if this integer is equal to a multiple of big N, 0 otherwise. It must be now, you use it, it's used a lot, okay? And so you basically place this summation, so this is its value, and so this will give you the discrete time delta, and the discrete time delta gives you 1 only when its argument is equal to 0. So basically only when small m is equal to minus n. You tell me, but the small m is not equal, small m is never equal to minus n. Okay, so actually you may be correct in complaining about how I wrote the output here. But if I write down the output like this, you know what I mean. It means The sequences we are dealing with are periodic with a period n. This is minus n. This is correct to write down. This is correct to write down. If you want your indices to only live between 0 and big N minus 1, don't worry. If I write down something like this, just write it like this. It's exactly like when we talked about time reversal. This thing is x of big N minus N. Okay, so get used to it. DFT periodicity. You have discreteness in time and in frequency. Then you have periodicity in time and in frequency. The sequences you are dealing with are periodic in time and in frequency. Okay, so the DFT of the DFT is n of x of minus n, or if you want to write it like this. Now, what is the meaning of something like this? Well, I mean, it has, of course, several meanings. One of them you will see in the homework. Another one is, suppose that you have hardware that is doing the discrete Fourier transform, and suppose that your hardware is just doing the discrete Fourier transform, not the inverse. So it's doing the discrete Fourier transform, not the inverse discrete Fourier transform. Should you panic? If I take the DFT of some signal and then do some manipulation in the frequency domain, then how do I get back to the time domain? Well, no problem. Do the DFT of the DFT. Okay, so you use your hardware to do the DFT. Use it again. But note that when you use it again, you will not get x of n. What you will get is big N x of minus n. So to IDFT a sequence, again, suppose that again, you just have a hardware that computes the Fourier transform, not the inverse one. Do the DFT. Go for it. Don't hesitate. But then once you get your output, time reverse it. Time reverse it, the trick that I talked about here. Okay, so if you have your samples arranged in this way, fix the first sample and then take the other samples and flip them left, right. And then divide by this big N. You will get your signal in the time domain. So to IDFT sequence, I mean, you can read something like this. Why? I mean, just do the IDFT. Well, some hardware is like this. They allow you only to do, or the opposite, by the way, you can just do IDFT, not a problem. The DFT and IDFT are very closely related, and you have a signal, you can obtain the DFT from the IDFT and vice versa. Typically, this will involve an operation of reversal, which is simple, by the way, to implement. It's just fix a sample and flip the other samples, and sometimes you multiply or divide by big N. So basically this is how you can get the IDFT if you are forced somehow to just use DFTs. What is the DFT of an upsampled signal? Well, the DFT of an upsampled signal, so you have a signal with n samples. What is the meaning of upsampling? So upsampling means that you insert big L minus 1 zeros between two consecutive samples, right? So this is upsampling as we know it from signals and systems. So L is an integer greater than or equal to 2. And if I upsample a signal, it means that if this is my original signal, between two samples I insert L minus 1 zeros. And so if you start with a signal with n samples, then after inserting your zeros, your signal becomes NL samples. So this is extremely important because there are some operations we do in signal processing in which the number of samples is manipulated, and so you need to adapt the expression of DFT or inverse DFT to take into account that you are no longer dealing with n samples. So upsampling is one of them. If you upsample a signal with n samples, what you do is that you take one sample from the n samples and then you append big L minus 1 zeros, and then you take another sample and you put big L minus 1 zeros, and so forth. So you end up with NL samples, a sample from the original signal followed by L minus 1 zeros, and so on and so forth. So now if I am taking the DFT, what should I write for the summation? Okay, so again, this is something that you need to make sure that you can write without hesitation. Summation, not from 0 to big N minus 1. Now my signal, I'm doing the DFT of the upsampled signal. I need to have, how many samples do I deal with now? Not N, NL, so NL minus 1. Then YN, then what? E to the minus I 2 pi, the number of samples, NL, then N, the same index here, then it chooses an index for the output. Let's say that it is K. Okay, very important, because now again you have NL samples, or again, like people in DSP typically call those guys points. So, you know, you hear people saying that we need here to take the NL point DFT because we have NL samples. You know, yes, most of them are zeros, but I mean, you know, 0 is a 0. I mean, it's something to be respected. 0 does not mean nothing in some sense. So you start basically using the DFT, and then you start basically manipulating this summation. So for example, you know that you know, most of the, if the index n is not an integer multiple of L, you have zeros, so you can eliminate all those terms from your summation, and you end up with summation in which you only have the index n is an integer multiple of big L, and then you want to express the DFT of y in terms of the DFT of x. So the way to go is the conventional way of basically changing your summation index. So we will say that v is equal to n over L, and when you do so, you get this summation here. And then you look at this summation, summation v from 0 to, I mean, so basically this should be n, this is an error, n minus 1, and xv e to the minus I 2 pi kv over n. Oh, that's the DFT of x of n. That's exactly the DFT of x of n. So does this mean that the DFT of the upsampled signal is exactly equal to the DFT of the original signal? In some sense, this is true. But remember, like for DFTs, they are designed such that, you know, if you start with a number of samples, you should get the same number of samples. So now the signal y, it's composed of NL samples, and so basically when you do its DFT, the index k must have, like, you know, it must go from 0, 1, 2 to NL minus 1. Yes, that's true. Okay, so this is not, you know, so here what we have is yk is equal to xk. Okay, so yk, so what is yk plus n? Okay, no problem. Yk plus n is equal to xk plus n, and remember, big X is an n-point DFT because signal x has n samples, so this is equal to x of k. What is yk of plus n plus 1? Well, it is equal to x of k plus 1. So it is, let's, x plus n plus 1, which is equal to x of k plus 1, and so on. Okay, and so basically, when I say that yk is equal to xk, and then you say, oh, we want a DFT of y that is composed of NL samples, not a problem. I mean, because your index k you can move it any way you wish from 0 to NL minus 1. And don't forget that the DFT of Y is in terms of the DFT of X. And the DFT of X is n periodic. Okay, so you should keep in mind DFT of M, so M points or samples is n periodic. Again, in many cases, I will just use big N, but this is an example, again, that I wish you spend good time understanding and tracking exactly what we are doing. You know, because you are doing an operation that basically manipulates the number of samples by inserting the zeros. And I will leave for you to read the other, like side of, in which like you downsample, and by downsampling, what you are doing is that you are throwing away samples. In both cases, what you do is that when I tell you take the DFT, then you adjust the expression of the DFT to the new number of samples. So if you have n samples, then you have a summation x or y or z of v from 0 to big M minus 1, e to the minus I 2 pi, v number of terms, and then an output here, let's say s. Okay, so again, train yourself to write down the DFT basically based on an understanding that does not depend on small n and small k and big N and so on, because in many cases you will have to adapt the DFT to situations in which we deviate from the original definition with big N and small k and so on. Very important. Like again, like it may sound like complicated or anything, but after a while, you'll find that actually it is nothing. Okay, so again, this is this part, and the part about downsampling is something that is worthy of investigation. Okay, perhaps this will be the last thing to say in the lecture, and if it takes too long, I will do it again, because like it's sort of extremely important for practical purposes, because the DFT is typically used for efficient implementation of convolution. And so typically what you do is that you have a signal x1 of n, x2 of n. So desired is basically x1 of n convolved with x2 of n. So what you can do is that you take x1 of n and DFT it. You get x1 of k. You take x2 of n and you DFT it, and you get x2 of k. And we know that in the frequency domain, you do what? You do multiplication. So you multiply these guys together. Multiplication. Okay, and then you do the inverse DFT. Right? Mathematically speaking, this is like, it seems like what we do in Fourier analysis. You want to convert two signals. One way of doing things is, you do things in the frequency domain. In the frequency domain, you do not really need to do convolution or anything. You multiply, and if you do the inverse Fourier transform, you get convolution. So this is something like, and it's actually one of the powers of the Fourier analysis, in which, like, rather than doing convolutions, like if you operate in the frequency domain, you just do products. And then whenever needed, you do the inverse Fourier transform to get the convolution in the time domain if needed. Okay, so what is the story here? So the story here is almost the same, but with a complication. And this means that if you are trying to use the Fourier transform, the discrete Fourier transform in practice to implement convolution, then there is something that you need to care about. Okay, so what is the story? What will happen if you take two DFTs, multiply them, and then do the inverse DFT? So what is the inverse DFT? So the inverse DFT So you start. So we have this product. It's a function of k. Now we are doing the inverse DFT. So I will take the function of k. I multiply by e to the plus. Okay, so because it's inverse DFT, 2 pi k over the number of samples. Here it's n. So I will write n, and then an index chosen for the output. I will just choose n. And in the definition we have 1 over big N. Okay, so basically in the DFT, the sum, you have the sum. In the inverse DFT, the sum is multiplied by 1 over big N. This is what we obtained from our derivation. Okay, so how can we do this? So one way is basically to take x1 of k and express it in terms of the signal in the time domain. Okay, in the signal in the time domain, you are left with another summation which gives you the other signal in the time domain, but it will be x of n minus m. Basically, the order of operations here, you can do the nice thing about DFT, it's like its math relies on finite sums. Okay, so there are no worries in basically interchanging the order of sums or anything. And so, we did something similar, for those who basically studied the DTFT. For the DTFT, you will have to worry about interchanging infinite sums, but we don't have this here because the DFTs have finite sums. And so you end up with this thing here. And then you look at this thing, we say, well, it looks like convolution. But there is a problem. What is the problem? The problem is that finite, it's finite. And so this is something, exactly, convolution, we typically do it with signals that are sort of, of time limited. But now, if you use the DFT mathematical machinery, your signals are periodized. Even if you do not intend them to be periodized, they will be treated as if they are periodic. Okay? So, in fact, what we get here is not the conventional convolution. It is something called the circular convolution of the two sequences. So if you have, a signal that looks like this and like that, and you want to do its linear convolution, the convolution that you are used to, then you take one signal, you time reverse it, you do time shifts, and for every time shift you get the corresponding output. And as someone said, basically if your signal has 3 samples, the other one has 3 samples, you get 5 samples in the output. But if you play the above game with the inverse DFT, it will not give you this result. It will give you something called circular convolution, which is, it's as if we take one of the signals and periodize it everywhere. So we take those samples 1, 2, 3 and keep repeating them to the left and to the right. And then we convolve. Okay, and in the next lecture, I will tell you why actually we have something like this. So again, we don't have time to basically explain this. My point is that if you take x1 of n, x2 of n, do the DFT of x1, do the DFT of x2, multiply x1, k, x2, k for every k equals 0, k equals 1, up to n minus 1. Do the inverse DFT. Don't expect that you will get the linear convolution. You will get something very related, but a bit different, called the circular convolution. And if in some application your concern is linear convolution, then you need to play a game with the DFT to convince it, or to trick it, if you want to say, to produce the linear convolution. And in many applications, we want the linear convolution, the convolution as you know from your previous studies. Okay? And so, you will have to, by the way, the game that we will play is not complicated at all. It's just, you insert zeros. Okay, so you do something called zero padding. Okay, so you can play. I mean, if you know, you can implement the DFT on MATLAB using FFT. You can play with these things. You know, generate a sequence, take its FFT, which is just the DFT implemented in a smart way, and we will study it in details. Okay, so you can basically play with these guys and make sure that before the next lecture that you understand the machinery, the mathematical machinery of the DFT.